Hey, what's up everybody? In this section of this course, we're going to go over the BFS or breadth first search pattern. Breadth first search means that we search the entire breadth of a level of a tree before moving down to the next level, starting with the topmost level of the tree. In other words, we will be traversing our tree in level order. A tree is just a set of linked nodes organized in a hierarchical way such that there is a root value and subtrees of children with a parent node. The way that we traverse a tree in a breadth first or level order manner is by making use of a queue. A queue is a data structure which is essentially a linked list where items are added and removed in first in, first out order. For example, here's what it would look like to add some items to an empty queue. If we were to remove an item from this queue, we'd remove the first one that was added, and we'd continue to need to add and remove items in that order like so. At this point, you're probably wondering how this data structure helps us to traverse a tree. Well, essentially what we do is we start by adding the root of our tree to our queue as the first item to be processed. When we remove this item from the queue to be processed, we then add its children from left to right to be processed in the order that they are added. And of course, the root's children make up the next level of our tree. So after processing our topmost level, or the current level, which contains the root, we move on to processing the next item in the queue, which is the leftmost item of the next level. And for the first and subsequent items of this next level, we will do the same thing. Add their children to the queue from left to right to be processed. But notice that since a queue adds and removes items in, first out order, the next level's items will not be processed until we finish processing the current level's items. And this process is repeated until we reach the final level of the tree. And that is how we traverse a tree in a breadth first or level order manner. So now let's see if we can apply this knowledge to our first problem. So the first problem that we're going to be solving is this binary tree level order traversal problem here, which can be found by filtering the Leetcode patterns list using the BFS category. So given the root of a binary tree, we're asked to return the level order traversal of its nodes' values from left to right. So essentially, each array nested within this larger array contains the nodes' values from left to right for each level. So this array represents this first level with the values being 3, and this array represents this second level with the values being 9 and 20, and so on and so forth. So to solve this problem, we're going to do a level order traversal of the tree, and for each level we will create an empty array. And as we traverse through each node of a level from left to right, we will just append the value for each node to the array. And after traversing each level, we will just append the finished array to the larger array, which will be returned once the function is complete. So let's go ahead and get into writing some code. Okay, so within our Python source coding interview patterns directory, we're going to make another directory called BFS. And then we'll just change directory into that BFS directory. And within this directory, we're going to make a directory called binary tree level order traversal. And we're going to also change directory into that directory. And from here, we're just going to set up our virtual environment. So we'll do this command here, venv. And now we have our virtual environment folder, so we can just go ahead and activate our virtual environment. And from here, we're going to just want to create a file called binary tree level order traversal.py. And within this file, we're going to need to first import deck from this collections module. So from collections, import deck. And this is what we're going to use to create our queue. And what we also need to do is we need to get the node class from the actual problem description. So we can just change this to Python 3, and we can take this class definition for a binary tree node. And we're going to use this example to make sure that our algorithm is working correctly. But for starters, let's just paste this into our code. And we can just uncomment this. And to start, we'll just create an entry point. So if name equals main. And we first need to build our binary tree. So the binary tree that's in the problem description, we're going to build it here. So this is what the binary tree looks like in the problem description. So we have a node that contains the value 3 for our root, and its left node is 9, and the 9 node has no children. And its right node is this node that contains the value 20, which has 2 children, which are these 2 nodes here. And the way that they represent it here is in an array-like structure, but it's actually a binary tree, so just keep that in mind. So we'll just go ahead and copy this over so we can know what numbers that we need to put into our binary tree nodes. We'll just paste that in here and comment that out. To start, we're going to need to create a head node, which is going to be a tree node from the class above, and it's going to contain the value 3. And then we need to set our head's left node equal to a tree node as well. But this one is going to contain the value 9, and its children, its left and right node, are both going to be none. So as you can see here, the values that we pass into this tree node are the value for the actual node, and the left node and the right node. And they actually default, the left and right node for the tree node actually default to none, but I'm just writing it in here to be explicit. So next we want to create our head.right, which equals another tree node, which is going to contain the value 20. And this right node actually has 2 children node, a left and a right node. So we're going to set the left node of this right node to another tree node, and the right node of this right node to another tree node as well. And this tree node, the left node of our head's right node, so this node here is the left node of our head's right node. So our head node, this head node's right node is this node, and then its left node is this node. So for the left node, the value is going to be 15, and then we're going to have a left and right child of none. And for the right node, the value is going to be 7, which will also have a left and right child of none. So here we'll put 15, none, none, and here we'll put 7, none, none. And this node is this node here. Okay, so now that we've actually created our binary tree, we can go ahead and just print the result of level order. And this is the function that we're going to create with our algorithm in it, and we're just going to pass in the head. So now let's go ahead and define this function. So we'll just define a function that we'll call level order. And to start, we just want to make sure our root is not none. So if our root is none, they want us to return an empty array. And actually, we need to take in the root parameter. And then we're just going to create a queue by using this deck. So this deck data structure, we're just going to use as a queue so that we don't have to create our own queue class. And the reason we can use this deck as our queue is because if we go to the documentation for this deck in our collections module, we see that decks are a generalization of stacks and queues, and decks support thread-safe, memory-efficient appends and pops from either side of the deck with approximately the same O of 1 performance in either direction, which is what we need. And we're provided with all of the necessary methods to work with a first in, first out queue-like data structure. So we can append, which adds the value to the right side of our queue or our deck, and we can pop left, which would remove and return an element from the left side of the deck, which is in line with what is necessary for a first in, first out flow. So once we've created our queue using our deck, we will go ahead and append our root to our deck or our queue. So we're going to insert our root node into our queue. And in the problem description, they want us to return an array or a list containing individual lists for each level of the binary tree. So if we go to our problem here, they want the output to look like this. So we have a list which contains individual lists for each level. So each individual list has the values at each level. So this top level is only one node of the value 3. So there's a list that contains 3. And this second level here is 2 nodes with the value 9 and 20, and etc. So that's what we need to return. So we're essentially going to need to return a big list that wraps all of these tiny lists. So for that very reason, we'll just name this big list and we'll create an empty list. And then we can start writing the code for the rest of the algorithm. We'll just do while length of queue. So this just means while there are still nodes within our queue, then we'll go through this while loop. But once there are no more nodes in the queue, then the while loop will terminate. We're going to set size equal to the length of queue. So what this is doing is this is getting the size of the level. So it's getting the number of nodes that are in the current level. And we need to get the size before we start to pop nodes off of the list, or then the size would be inaccurate. And then we're going to create small list, which is going to be the array or the list for the individual list within the big list. And then we're going to do a for loop, and we don't need to use the variable. So we'll do for underscore in range, and we'll do size. And for every node within the size of the current level, we're going to do node equals queue.popLeft. So we're going to pop that node, or pop the first in node off of our queue. So the leftmost node, we're going to pop it off of the queue. And we're going to append the value of that node to our small list. And then we're going to check if that node has children. So if node.left, queue.append, node.left. So if there's a left child on our current node, we want to add it to our queue so it can be processed in the correct order or in level order. And then if node.right, we're going to do the same thing. Queue.append, node.right. And once we've finished doing this for every node within our level, we're going to exit the for loop and we're going to append our small list to our big list. And we're going to do this for every level of our binary tree. And once we're done with every level of our binary tree, we're going to return our big list. And that's going to be it for the algorithm. So let's go ahead and test this. We can just save. And what we're expecting to see is, we're expecting to see an output that looks like this. So we can just go ahead and do Python 3, binary tree level order traversal.py, and we get an error, level order is not defined. So let's go back in here. And we forgot an L here. And let's just make sure. Yeah, we're good to go. So we'll just save that and run this again. And as you can see, we get the expected output of a big list containing the little lists for each level of our binary tree. Now let's go ahead and get into our visualization of this algorithm. Okay, so let's get into visualizing this algorithm. We'll start by drawing out our binary tree. So we'll just draw our binary tree here. And the values are 3, 9, 20, 15, and 7. And we're going to start by calling the function passing in the root of this binary tree. And the first thing that we do in this algorithm is check to see if our root is equal to null. And if it is, we're just going to return an empty array because that's what's expected for the problem. But if that's not the case, we'll move on to creating our queue using this deck data structure. And we can just draw out our queue here. And then we're just going to append root to our queue. So we're going to append this node to our queue. And from there, we're just going to create a variable called big list. So big list is going to be the array that we return. So we'll do big list. And big list is going to be an array containing multiple smaller arrays. And each smaller array is going to contain the values or the nodes at each level. So for example, this first level, we're going to want to append a small array containing only the value 3. And then this next level, we're going to append another small array containing the values 9 and 20. And you'll see what I mean by that in a second. So then once we create our empty big list, we're going to end up at this while loop where we're just going to continue to run this while loop while our queue is not empty, essentially. So the first thing that we need to do is we need to set our size equal to the length of the queue. And this size is going to be how we keep track of what level we're on. Because at the start of this while loop, our size is going to be equal to the number of nodes in the current level. So for example, in the beginning of this function, when we first start to run this while loop, our size is going to be 1. It's going to be 1 because our queue only has one item in it. So our size will start as 1. And then we'll also create a small list. So we'll create a small list, which is going to be an empty list as well. And then we're going to iterate through our size. So we need to do this because we only want to iterate through the current level. So our current level only has one node and our size is 1. So we'll iterate one time and we'll pop this node off of our queue. So we'll pop 3 off of our queue. So let's pop it off and we'll put it here so that we can know that that's the node that we're dealing with. So node is this. And then we're going to append to our small list the value for our node. And the value for this node is 3. Because if you remember from our code, our node class looks like this. We have class, node, and node has a value and a left and a right. So this node 3 has the value 3 and it has a left node and a right node. Its left node is this node and its right node is this node. So what we're appending to our small list is only the value, so 3. So we're going to append 3 to our small list. And then we're going to check to see if this node has a left node, which it does. And if it does, we're going to append that node to our queue. So we're going to append to our queue this node's left node. So we'll append that here. And then we'll check to see if our node has a right node. So this node or this node has a right node, which is this node here. So we're going to append this node to our queue as well. So we do that. And then we're going to append our small list to our big list. So this is our small list. We want to append it to our big list. So we'll just go here and put our small list here. Sorry, that's a comma. So that's our small list. And then once we finish that, we're not going to continue with this for loop because size was only 1. So we only do one iteration. And then we're back up to the top of our while loop. And the length of queue is still not 0. We have 2 items in our queue. So we're going to set our size equal to the length of queue, which is 2, 1, 2. So our size is now going to become 2. And as you can see, we just finished this first level, right? And now we're on this second level. And our queue contains the 2 nodes for this second level only. And the size of our queue is 2. So we're going to iterate through 2 items because we only want to iterate through the nodes in this level. So that's why our size is so important, because the size is always going to be the number of nodes on the current level when we first start this while loop. So then we're going to have our small list equal to an empty list. So we can just erase that 3. And once again, we're going to iterate through our size. So this time we're going to do 2 iterations. So for this first iteration, we're going to set our node equal to queue.popLeft. So we're going to pop this node off of our queue. Because remember, queue is first in, first out. So we're going to pop this one off because this is the one that got added to the queue first. So we do this. And let's erase this too. So now the node that we're working with is the one that contains the value 9. And we're just going to append to our small list this node's value. So this node's value is 9. So we'll append that to our small list. And then we're going to check to see if this node has a left node. Does this node have a left node? No. So we're not going to append the node to the queue. Then we'll check to see if this node has a right node. Does this node have a right node? No. So we're not going to append the node to the queue. And then we'll go back to the top of the for loop again because remember our size is 2. So we need to do one more iteration. And And once again, we're going to pop left. This time, the value that's at our leftmost item or index in our queue is 20. So we'll pop this 20 off. So this node is the node that we're dealing with now. And we're going to just append the value of this node to our small list. So we have 20 here. And then we're going to check to see if this node's left node exists. So does this node have a left node? Yes. So we're going to append it to our queue. So this goes to the queue. So we have 15. Then we'll check to see if this node has a right node. So does this node have a right node? Yes, it's this node. So this node also needs to get appended to the queue as per this line here. So 7. And now we've iterated twice and our size here was 2. So we no longer need to continue with this for loop. So we're going to end up at this line here where we're going to append our small list to our big list once again. So now this gets appended here. So we'll go like this, try to make some space, and we'll do 9 and 20. And back up to the top of the while loop once again. And once again, we still have 2 items in our queue. So we will continue with this while loop, and our size is going to still be 2, 1, 2. So we'll just leave this, and small list is going to be empty. And once again, we're going to iterate through our size, and we're going to pop the leftmost node off of our queue. So we're going to pop 15 off. So let's erase that. We'll pop 15 off. And we're just going to append this node's value to our small list. So the value is 15, append it to the small list. And then we're going to check if this node has a left child. It doesn't, so we won't do this. Then we'll check to see if this node has a right child. It doesn't, so we won't do this as well. So we just end up right back at the top of the for loop again for one more iteration, because remember the size is 2. So now we're going to pop our leftmost node off the queue once again, which is only this 7 is left. So that's going to be the one that we pop. And then we're going to append this node's value, which is 7, to our small list here. So we'll append that, and then we'll check to see if this node has a left node. It doesn't, so we won't do this. And then we'll check if this node has a right node. It doesn't, so we won't do this. And at this point, we're done with this for loop because we did 2 iterations and our size is only 2. So we'll end up back down here where we will append our small list to our big list once again. So this list is going to get appended here. So we'll do that, and 15 and 7. And this while loop is going to terminate at this point because our queue is completely empty, as you can see. And at this point, we're just going to return our big list, which is going to contain an array for each level. And each miniature array is going to contain the values for all of the nodes in its corresponding level. So this array is for this level and it contains the value 3. And this array is for this level and it contains the value 9 and 20, 9 and 20. And this array is for this level and it contains the value 15 and 7. And I'm sorry I keep calling these arrays, but in Python I understand that it's list, so I apologize. And that's going to be it for visualizing this algorithm. So now let's go ahead and get into our time and space complexity, starting with our time complexity. So our time complexity is going to be O of n, and that's because, as you were able to see, we need it to touch each node of our input tree exactly once. So our time complexity is going to scale linearly with the size of our input tree. And as for our space complexity is also going to be O of n. And that's because our queue in the worst case needs to hold n nodes. So for example, for this tree here, at most our queue is going to hold the size of one level, right? So at most our queue is going to hold 2 nodes. And in total we have about 1, 2, 3, 4, 5 nodes here. So 2 nodes out of 5 is roughly half. So let's just say that we're holding O of n divided by 2 roughly. And in this case, we'd still just ignore this division by 2 because it's a constant, and we'd still be left with O of n. And you might say that 5 divided by 2 isn't exactly 2, it's 2.5, but still it doesn't actually matter when we're talking about big O. And you could also have a situation where the nodes look something, the tree looks something like this. And at most, the queue would need to hold 2 nodes. So in this case, it would look something like O of n minus 1, because n is 3, but at most the queue only needs to hold 2, so 3 minus 1 is 2. But even still, in that case, we would still ignore this 1. So this would still be O of n. So yeah, our space complexity is O of n. I hope that makes sense. And that's going to be it for this visualization. If this was helpful to you, please don't forget to like and subscribe if you haven't already, and I'll see you in the next one.